Consecutive streak and gap detection is fundamental for calculating cohort retention, detecting session inactivity bounds, tracking engagement milestones, and attribution modeling in modern analytics warehouses. Calculating consecutive streaks in temporal logs is a classic SQL design test. Our goal is to find the longest consecutive login streak for each user in our activity records. While this sounds like a basic count, candidates frequently crash into an O of n squared self-join trap, or struggle to isolate true streak boundaries when date gaps occur. Let's trace why. Here's the trap: joining the activity table to itself on user ID and a range predicate to count consecutive days. This query joins each login to every login within a 30-day window. While looking correct for small datasets, it triggers a massive quadratic scan and fails to detect when a streak actually breaks. Why is the self-join approach catastrophic? Because inequality joins force the database engine to execute nested loops. For a large activity log, this requires millions of row-by-row comparisons. Worse, it doesn't isolate contiguous blocks, meaning overlapping date windows are counted as single continuous streaks. To solve this efficiently, we apply the gaps and islands technique. First, we deduplicate activity dates using a distinct subquery. Next, we use the row number window function sorted by activity date. Subtracting this sequence number from the calendar date produces a constant offset group key. Contiguous dates subtract to the exact same date, forming our streak islands. A critical senior follow-up is applying this exact gaps and islands template to enterprise analytics. In production, this pattern maps directly to marketing touchpoint attribution streams and cohort sessionization pipelines, isolating sequential events. We must also handle date gaps using LAG. By checking if the difference between adjacent deduplicated dates is exactly 1, we assign streak IDs cleanly without nested loop overhead. Lock in this gaps and islands blueprint. Avoid O of n squared self-joins that crash at scale. For consecutive streaks, deduplicate inputs using distinct, then subtract row number from dates to group contiguous logs. For gap detection, verify offsets with LAG. Master this, and you will pass your system design loops. Let's analyze the naive self-join trap approach. Time complexity, O of n squared. Space complexity, O of n squared. Performs an unconstrained self-join on temporal ranges, checking every login against all subsequent logins per user, resulting in n asterisk n1/2 comparisons. Let's analyze the row underscore number subtraction islands approach. Time complexity, O of n log n. Space complexity, O of n. Sorts and scans the deduplicated records in linear logarithmic time, utilizing a single pass window scan to calculate constant offset groups in memory. Let's analyze the LAG gap detection approach. Time complexity, O of n log n. Space complexity, O of n, scans consecutive rows in a single pass to flag gaps where date difference is greater than 1, computing contiguous streaks without self-joins. The interviewer will then ask, what happens if a user has multiple login actions on the exact same date? We must deduplicate the active dates using a distinct CTE. If duplicates remain, the row number increments without the date incrementing, breaking the offset group key. The interviewer will then ask, how does the omission of the order by clause, inside over, affect lag and lead functions? Without an order by clause, the database engine returns records in a non-deterministic order, making the offset calculations meaningless and leading to wrong results.